Hello everyone, welcome to the session on electromagnetic fields and transmission lines. Myself Dr. Sohail Rana, and today we will continue our last discussion which we closed on the potential. So if we go with the summary of this chapter, we have discussed about the current and the definition of current. We imagined a current component in 3D for simplicity, and we considered them as big spherical balls, but actually the electrons are considered as small point charges. For simplicity, we are considering them as a spherical ball. If we extend the point and if we zoom it, we get a shape of a sphere. And for point charge derivation also, we consider spherical coordinate system. Then we discussed about the insulator, dielectric and conductors. We discussed about the conventional direction of current and the actual direction of current. Actual direction of current is from negative terminal of battery to the positive terminal of the battery, like this. That is the flow of electron. But conventional direction of current is from positive terminal to negative terminal. We have also seen the direction of electric field intensity is from positive to negative. That means it is in opposite direction to that of flow of electrons. Then we defined 1 ampere current. 1 ampere current is nothing but it is 1 coulomb of charge. If crossed in 1 second, we say that 1 ampere of current is generated. Right. Then we discussed about the current density. Current density is the ratio of current to surface or volume. This could be according to the situation of the charges present. Charges may be present on a surface or they may be present in a volume. So here we can imagine a surface charge, a volume charge constituting a volume, constituting movement of volume is making some volume charge density related to volume current formula. Then we discussed about the different densities of the current densities. Then we derived conductivity. We discussed relation between J and rho v. Continuity equation we have discussed. Relaxation time we have discussed. Then dielectric materials we have discussed. In that we have discussed about the polarization and dipole. The concept of polarization and dipole we have discussed in this topic. Then after that, the generation of dipole we have seen inside the atom, which becomes like a small capacitor. Then dielectric constant we have discussed, various types of materials. We have discussed about potential, the derivation of potential, relation between V and E for the potential. So after that we have seen some examples. Then we have seen the relation between E and V. So now we will see the conservation field for Maxwell's equation. Now this time we have to discuss what is the conservation for Maxwell's equation. Now what is meaning of conservation law of energy? Conservation is something we say that energy cannot be created nor destroyed. If we do some work in a closed path, that means net work done will be equal to 0. That is what it says. So we will see how mathematically this thing is represented. Say Okay, now we consider that we have some point P and another point Q. There are 2 points. Now if we consider there is some voltage VA and we make a closed path and come back to the same point, then what we can say, the VA minus VA is nothing but 0. What is voltage? For voltage we have seen the relation with E. What is voltage? Voltage is nothing but E bar dot dl bar. So now if we keep that, so what we can say, if the integration limits are from A to A, the line is closed. This is single integration for line. So this line is a closed line. So what we can say for that? We can say if we are going from A to A, and if we calculate electric field intensity for this closed path, that will be nothing but equal to 0. So this is nothing but VA. Suppose there is VA, this point is some VB. If we are using it in a circular line, so what we can say? We can say VA minus VB is equal to integral of E bar dot dl bar, right? So this is nothing but Maxwell's first equation, we can say. When this one is possible? When VA is equal to VB. So this is about this. So what is general expression for voltage? Voltage is equal to integral of E bar dot dl bar. So now let us check the units. So unit for this potential. So fine. So what we have? We have voltage is equal to integral of E bar dot dl bar. And last time we have also derived that. What we have derived? That E is directly related with dV by dr. Now if we equate this with electric field intensity, what is formula for electric field intensity? It is Q upon 4 pi epsilon naught R square. But what is the formula for voltage? For voltage, the formula is Q upon 4 pi epsilon naught R. Now what is the difference between these two? The difference between these two, we have to realize that E can be given as vector. So we can write it as E bar. Here we have to add the direction component AR cap. And what is voltage? Voltage is a scalar quantity. This voltage is a scalar quantity and this one is a vector quantity, right? So now from our earlier discussion, let us discuss the equipotential surface. Now let us consider this 3D diagram. Here we are considering one charge, a very big charge present on surface, we are equating it with the earth surface. So what is this? Suppose this is equal everywhere, then there will be electric field lines always perpendicular to the surface of charge. If we consider this one as the charge, all the electric field intensities will be perpendicular to the charge. Now if we consider that there is the movement of voltage across this surface where this electric field intensity is perpendicular in all the direction, then we consider it as equipotential surface. So then this is the equipotential surface. So equipotential surface is also very important concept we have to realize, because most of the time we consider the equipotential surface. Always we have to remember that electric field intensity is always perpendicular to the surface who is creating it. The most basic component who creates it is a charge. So suppose if we consider two charges, one is say positive charge and another one is say negative charge. So electric field intensity will be always going outward in perpendicular distance from this charge, right? And this one will have all the force lines going inward, right? So this is about the electric field intensity directions, and it is always perpendicular. Now one more thing, if we add, as these lines go away from the origin, the distance between them increases. So for the viewer, if suppose we are viewing from a far distance, so when we view towards the source, we feel that these two lines are coming as perpendicular because they go for very far away region. So if someone see that the light, suppose light is also an electromagnetic wave, so someone may feel that they are the parallel lines coming from the source, but actually they are perpendicular to the source. Okay, now we will see its relation with del. Okay, now what we know that so far, we know that E bar is nothing but, we can say it is a derivative of minus derivative of dy by say dx. Now if we consider a three-dimensional view where we have x, y as well as z. So what we can say? We can say that we can write it in the form of three directional components. So say E will be equal to minus say dou V by dou x ax cap plus dou V by dou y ay cap plus dou V by dou z az cap. Now what is unit of electric field intensity? Unit electric field intensity is defined as force per charge. Unit of force is nothing but newtons. Unit of charge is nothing but coulombs. So unit of electric field intensity is newtons per coulombs. So that is what we get. Now out of this term we have discussed one del operator. What is del operator? Del operator is dou by dou x into ax cap plus dou by dou y into ay cap plus dou by dou z az cap. So if we replace this term with del operator, so what is del operator? Once again I will write here for simple remembering. The del operator is vector spatial operator who represent the terms in 3 dimensions. So it is given by dou by dou x ax cap plus dou by dou y ay cap plus dou by dou z az cap. Now this complete term we can replace with the del operator. So what we can write for here? For this, electric field intensity will be equal to minus del dot V. This is another approach for deriving the relation between E and V. So this is, say, in other words, what we can say for this? Say, in other words, we can say E is equal to negative of gradient of the voltage. So here what is our take out? Say E bar will be equal to minus of del dot any scalar is nothing but minus of gradient of V. So with this we'll continue another topic where we will see the voltages due to various charge distribution. So we have to find out voltages due to various charge distribution. Right. Now first one we will see for electric field intensity. We have seen what we have seen. We have seen various cases. Electric field intensity due to a point charge, then electric field intensity due to a line charge, electric field intensity due to surface. We can also have electric field intensity due to volume. In similar way, we can find out the voltage for different or various charge distribution. So let us consider the formula. What we have, we will write down the relation between voltage and electric field intensity. The first one is V, voltage between two different points. Say VAB is equal to nothing but E bar dot DL bar, or we can say VAB is equal to Q upon 4 pi epsilon naught R. Now what is this expression? This expression gives the formula of voltage because of a single point charge Q. So this expression is nothing but the equation for point charge. Now what is the line charge? If we focus on the definition of line charge, what we can say, line charge is nothing but combination of so many charges. They are arranged in a line, right? So now we don't have a single charge but group of charges present in a line. So its density is considered as rho L. So what changes we have to make? In place of line, in place of point, now we have to consider a line. We have to put the limit for the line. So for line charge, if you want to find out VAB, we can modify this same expression. Just in place of Q, what we will keep? We have to see what is rho L. What is the relation between rho L and Q? What is the relation between rho L and Q? Rho L is line charge density. Any density is given by the cos. The cos of line charge is Q by some length dl. So we have say dq by dl. So from here what we can say, dq is equal to rho l dl. As we are taking integration, we have to consider dq. In place of dq, we will keep rho l dl, and denominator will be as it is 4 pi epsilon naught r. So with the help of this expression, we can find out voltage for the line charge distribution. So similarly, what we can do, we can find out the line charge density for surface. What will be the difference? The only difference will be, now we have to consider surface charge density. Surface charge density is equal to, what is it, caused by surface. So it will be equal to say dq by ds. So dq will be equal to rho s ds. So VA we can find out as integration of, you will get double integration now, rho s ds divided by 4 pi epsilon naught r. If we solve this, we will get for the surface. Now for volume, what is there for volume? For a volume charge, how much charge is enclosed in this? That is rho v. That is nothing but the charge dq divided by differential volume dv. So from here what we can say, dq is equal to rho v into dv. So how we will find out voltage? Voltage will be equal to rho v dot dv divided by 4 pi epsilon naught r. So there is a dv, so we have to take a volume or triple integration. So this is all about voltage. Now next session we will start a topic called capacitors, and we will see what are the capacitor types and how much important it is. Thank you. Have a good day.